Looks like we're good to go, Peter.
Okay. Hi, everyone, and thanks for tuning in to this week's Quantum Chaos Seminar. So this week, it's my great pleasure to introduce today's speaker, Monica Schleier-Smith. She is currently faculty at the Stanford University, where her lab has been doing a lot of really interesting work on highly entangled states in cold atoms. She's won various prizes for her research, including the 2019 Presidential Early Career Award for Scientists and Engineers, and most recently, she's been the recipient of a MacArthur Fellowship. We're really excited to have her here today, and she'll be presenting about optically programmable interactions for quantum simulation. All yours, Monica.
Thanks so much for the invitation to, I guess, be here wherever that is virtually. The title of my talk is indeed Optically Programmable Interactions for Quantum Simulation. Before I start, maybe I'll just mention that I will be happy if there are questions asked along the way to keep this a little bit interactive. So I hope that you all will interrupt me if there are questions. Right, so in some sense, the kind of motivating vision behind what I'll talk about today is the dream that we might one day have in the lab, something like an arbitrary waveform generator for quantum engineers. So what I would love is a device where I can say, today I would like to study a particular Hamiltonian or start from a particular quantum state and press some buttons and press play and there it is. Now that might sound a little bit far-fetched, but there's been really a lot of progress in the past few years in building increasingly programmable quantum systems in the lab with laser-cooled atoms. So here are a few pictures from around the world of experiments where it is possible, for example, to position individual atoms in optical tweezers, in one-dimensional arrays, two-dimensional arrays, even 3D structures. This is sort of just one illustration of kind of the power of having a system that you can control with laser light. Now, in order for this to give rise to interesting quantum physics, we need not only control over the positions, but also to be able to have some interactions between the atoms. And in particular, one wants to have interactions that are long-ranged in the sense that means sort of long-ranged compared to the scale on which one can optically position and detect them, which is essentially the micron scale. So the focus of my talk today will actually not be on this aspect of fine control of the atomic positions, but on a complementary problem, which is how does one advance control over the interactions between atoms? And in particular, we're kind of inspired by this high level of control you can get with light. And we'll be asking the question, to what extent can we program the interactions between laser-cooled atoms with light? And so just to give a flavor of reasons why we're interested in this in my group, we're motivated by a few different directions, ranging from quantum control. Can we engineer interactions that give rise to useful entangled states that might have some applications ranging from quantum-enhanced sensing to computation? Can one perhaps program interactions that encode a particular computational problem and use the quantum system to help solve that problem? Or what I sort of advertised in the title of my talk, can we use these systems as quantum simulators to study phenomena in fields ranging from condensed matter to quantum gravity? And in particular, I would say, there's a wealth of sort of highly creative theoretical work where one writes down a Hamiltonian and tries to analyze what its properties are. But in many cases, there's not a physical system where you actually can realize it in the lab and answer questions in a regime where you can't calculate them. But we'd like to expand the range of models that one can realize in the lab for directions in quantum simulation. And so I will, just as a quick warm up, I'm actually going to give one example from this sort of bottom corner here of optimization, encoding problems in a quantum system. But then we'll also move on to directions in quantum simulation. Okay, so just as kind of an example of what kind of a thing might you want to do if you were going to build a quantum system and apply it towards solving even just a classical problem, right? So here's a classical problem that you may have encountered. when you go grocery shopping, which is that you walk out of the store with a bunch of objects with different weights. And you would like to know, you'd like to carry them in a convenient way where you're carrying the same weight in both hands. So you'd like to know, given these n objects with some weights, xi sub I, is there a way of partitioning them into two groups that would balance a scale? So that in a certain regime, that problem is actually NP complete. If you wanted as a physicist to solve it, of course, what you would do is you would express this as a spin problem. So you would say, if an object is in the green bag, I'll think of that as a spin pointing one way. If it's in the white bag, I'll think of it as a spin pointing the other way. Each one has some weight. And so the thing that I'm trying to minimize is some imbalance, which I'll write as some weighted sum of the spins of these individual objects. So you might want to minimize that, or maybe you would want to minimize equivalently. You could minimize the square of that. And that would look like actually some interacting spin model, where I have some couplings Jij between these spins, Szi, Szj. In this particular the case, the couplings have a certain form where they're products of weights. And at the end of the day, I get some sort of an interaction graph that you would like to sort of be able to program into your quantum system if you want to ask the question, can the quantum system help you solve this? Okay, so the tools you need to start to explore these types of problems are something you can encode a spin in, that will be an atom for us, long-range interactions, and some programmability of the interactions. So in my lab, we actually work with two different physical systems that give us these tools in slightly different ways. I'll spend the bulk of the talk talking about a system where we use actually photons to mediate interactions between cold atoms. So we trap atoms in an optical resonator, and we can send in light that can basically let any atom talk to any other atom. This allows you to have sort of highly connected interaction graphs, interactions that are highly non-local, sort of like the one I showed on the previous slide. And then towards the end, I hope I'll also have time to tell you about a system where we're generating optically controlled interactions by coupling atoms to Rydberg states. Those are more local in character. That's sort of natural if you want to study, let's say, spin chains. So depending what you want to do, either of these might give you the right type of model and some optical control of the interactions. So so let me start again. I'll talk first about these photon mediated interactions. They're highly non-local. And one of the directions that motivates this form of interaction are actually realizing kind of exotic toy models for quantum gravity. So this brings us to this sort of corner of quantum simulation. Quantum gravity is not the easiest thing to probe in tabletop experiments. But the fact that we sort of think we might be able to make progress in that direction is sort of inspired by the concept of holographic duality. And this is essentially the idea that space-time geometry is something that actually can emerge from entanglement in the quantum system. So that there's some mapping between a quantum system in, let's say, d spatial dimensions. In this picture, d is 1, and a system with one additional dimension and gravity that sort of curves space, and that curvature of the space encodes something about the entanglement properties. So, you know, that's a sort of a fascinating idea. I like this idea because it suggests that there might be some system that quantum mechanically looks very complicated. It's strongly interacting. It's hard to calculate what its properties are. But in some cases, there's some simpler picture where gravity gives you some way of sort of visualizing the structure of these quantum correlations. So that kind of raises all kinds of questions. You know, could you build simple model systems where you could probe this idea of an emergent geometry? Can models that have a simple description on the gravity side provide a starting point for understanding sort of a wider range of quantum many-body systems? But sort of as a starting point for even exploring this, it's useful to think about the simplest possible system from the gravitational perspective, which is a black hole. And it has been pointed out in recent years that a black hole can be thought of as the holographic dual of a maximally chaotic quantum system. So that is to say, if I had a quantum system where information that I sort of initially is encoded in 1 qubit can spread exponentially quickly across all degrees of freedom, then that would be potentially, under this duality, the analog of a black hole. So certainly one requirement to sort of address the black hole information problem, and it's actually a requirement that information in this quantum system would have to spread exponentially quickly. And you might ask the question, is this a process that can be studied in the lab? And it would be interesting to be able to study it also because this fast scrambling actually is really a fundamental limit on the dynamics of any quantum system. Okay, so what would it take to study that in the lab? Well, the challenge is that typically in sort of most systems that we build, information sort of propagates in some way that is governed typically by local interactions. In particular, if I have short range interactions, I'll have some light cone for the information, the spreading of information, where the time to reach a given point would be linear in the distance. Or even if I have some long range power law interactions, the time will still scale polynomially in the distance. And so in order to get something where you have an exponential spreading of information, where the time is only depends on the logarithm of the distance, you need to somehow go beyond these sort of natural forms of interactions and arrange a system where you have highly non-local interactions. And so this is an example where theorists can write down models on paper that they understand to behave in this way, to be fast scramblers, such as this Sachdev-Yekitayev model, which looks very exotic from an experimentalist standpoint. I have some fermions that can sort of hop in a correlated fashion in a completely non-local way. That is theoretically understood to be dual to a black hole, but does not look so natural to realize in the lab, although I should say there are some proposals. But something that actually turns out to be very natural for us in the lab is, it's not exactly this model, but it has a similar flavor. And that is to have not massive particles that hop in a non-local way, but actually spin excitations that can hop. So the basic idea is that we're going to have a system where we can start with one atom and spin up and one atom and spin down, and have a process where this atom, these two atoms exchange their states, which I can think of as sort of an excitation that hopped from one to the other. And it turns out that if that spin exchange process is mediated by light, it can be highly non-local. Okay, so the concept is, what I would like to do is have a system where this atom on the left can change from spin up to spin down by emitting a photon, and this atom on the right can absorb that photon and end up in spin up. In the lab, in order to have that photon absorbed by the other atom with high probability and not just fly away, we put everything inside an optical resonator, so two mirrors around the system. And we also want to be able to control this process optically. So the way we implement this is we have basically a Raman process, so a two-photon process where we have a drive field that's shown here in purple. And the drive field can drive a process. Oh my gosh, I should have muted my phone. I'm going to turn this off so this doesn't continue. I apologize. Okay, so a phone should always be put in do not disturb mode or turned off during a talk. But I forgot that.
That's a good takeaway.
So yeah, that's the lesson of the day, if you take nothing else away from this talk. Okay, so we want to have these optically controlled spin exchange interactions. And so we drive a Raman process where by turning on this control field, you drive a process where the atom absorbs a photon from the control, flips its spin, puts a photon in the cavity. Another atom can absorb that photon and flip its spin. And so then the spin excitation is hopped from one to the other. Okay. So that's the concept. And I should say this general concept of having some form of interaction mediated by photons in a cavity is fairly well established by now. So there have been experiments, both sort of motivated by quantum control, using these kinds of long-range photon-mediated interactions to generate entangled states, for example, squeeze states with applications in quantum metrology. And also in the direction of quantum simulation. So for example, using these long-range photon-mediated interactions to realize exotic phases such as supersolids. One key thing that we're doing that's fairly new is actually combining these long-range interactions with the ability to sort of locally manipulate and detect the system in order to probe dynamics. So the experimental setup looks roughly like this. This is literally like two mirrors 5 centimeters apart. We trap a cloud of atoms in between them in a standing wave. So you should think of the atoms as being sort of spatially, essentially pinned And the dynamics are purely in the spin degree of freedom. In the first experiments I'll show you, it's just essentially a sort of millimeter scale system of atoms, and we will sort of watch the spin dynamics within this cloud. So for example, and I'll typically sort of integrate along the transverse direction and just show you things as a function of position in the long direction. So here's an experiment where the vertical axis is time. At t equals 0, we turned on a control, before t equals 0, we initiated some spin excitations in a particular region of the cloud that I call A. At t equals 0, we turned on a control field, which led these spin excitations to sort of hop over to some other region and back. If you take cuts through the cloud, you'll see oscillations, showing there's some coherence in the system. And one thing you might ask is sort of, why do the spin excitations hop from A all of a sudden over to here, to this place I call B? You might expect them to just sort of travel linearly outward from A instead of suddenly showing up somewhere else. But it turns out this is something we can understand very well if we just take into account the fact that there's essentially an all-to-all interaction. Any spin can talk to any other. And we know something about locally the strength of coupling of each atom to the cavity mode. In this particular setup, actually, the atom-like coupling happened to be strongest in region B, and that was why the excitations first show up over there. So this is, we can realize this sort of non-local hopping of the spin excitations. It's so far not exactly yet a function generator, right? The forms of these couplings are basically given by something about the local intensity of the cavity mode. So broadly, we would like to be able to venture beyond this. And so there are a few different knobs we would sort of like on our function generator. One might be the spatial structure of the interactions, right? And so in what I showed you so far, it's kind of an all-to-all structure of interactions with this kind of product form. That turns out to actually have some interesting properties. It's not a fast scrambler, but it's actually, there are interesting aspects to the slowness of the thermalization in this system, at least theoretically. You might also, what are a few other examples of spatial structures we might want to realize? One-to-all might also be something natural and interesting to realize. That actually turns out to be relevant to solving this partitioning problem that I showed before. And if you're curious, you can read more about that on the theory side here. Maybe you'd like to have your atoms interacting as though they were leaves on a tree graph. That turns out to have some connections to fast scrambling that I'll say a little bit about later. Or maybe you want some kind of an interplay of local and long-range interactions. There's also recent theoretical work on models that have both local and long-range interactions as being interesting for fast scrambling. If you have sort of this central spin model plus local interactions, that can also be applied to measure certain properties of chaotic systems. So for experts such as the spectral form factor, there are proposals for this. So, okay, so we'd like some programmability of the spatial structure of the interactions, but also the form of the couplings. Do we have these spin exchange couplings, which I said I can kind of think of as this non-local hopping, or do I maybe also have an Ising coupling, which would be kind of an interaction in addition to that non-local hopping? And maybe I'd like to control the sign of the interaction. Is it ferromagnetic or anti-ferromagnetic? So those are all some knobs we'd like. I'm going to start with these last two, actually, the form and the sign of the interaction, for the case of sort of the simplest spatial structure that we naturally get in the cavity, which is couplings of this product form, okay? And then we'll come back to the spatial structure. So actually exploring sort of tunability of the form of the interaction, this sort of Ising versus XY, is something that was actually inspired by a collaboration with the group of Ehud Altman, who was thinking together with my student Greg Benson, was working with Ehud Altman's group to understand what is kind of the phase diagram of this sort of dynamical phase diagram of models that one most naturally realizes in these cavity QED systems. So it turns out even if you have this simple kind of product form of the couplings between any two spins, if you have the ability to tune the strength of the spin exchange coupling and the Ising coupling, one expects a rather rich phase diagram where the model is expected to be integrable in the case where one has either a pure XY model, so JZ equals 0, or an isotropic Heisenberg model. In between, there are some interesting regimes where classically the system looks chaotic, But quantum mechanically, well, I'll say that the theorists labeled this region integrable star. And I took the star to mean that they don't fully understand it, but it exhibits some sort of slow thermalization. So anyway, so that was kind of a motivation to be able to explore this phase diagram. And we realized in discussing this that actually there is a really natural way to tune in this system independently the Ising coupling and the spin exchange coupling, simply by actually controlling the orientation of a magnetic field relative to the axis of the cavity. And so roughly the concept is that the spins couple to the light via a sort of a Faraday effect. The magnetization affects the polarization of the light, and that acts back on the atoms. The quantization axis that I'm choosing for my spins is the magnetic field axis. And if the magnetic field were, let's say, along the cavity, then only the Z component of the spins would couple to the cavity. That would be the Ising case. If it's perpendicular, the X and Y components are sort of rotating through the Larmor precession, and they both couple to the cavity, and you end up getting a spin exchange interaction. And anywhere in between, you can basically tune JXY versus JZ. And while we're at it, also, we can tune the sign of the interaction simply by controlling the frequency of a laser field. So that's kind of shown here on the right, the tunability of JZ versus JXY as we vary a field angle, and also both possible signs. This is a summary, but to give a flavor for how we actually measure these things, what we typically do in the experiment, if we want to sort of map out what Hamiltonian do we have, is we'll prepare some spin texture in the cloud and watch how it evolves. So for example, we can prepare the spins at the left here pointing along the minus Z direction, these pointing along X and minus X. And if I have an Ising interaction, then I would expect actually, and it's non-local, so I would expect these spins that are in the XY plane to precess about the spins along Z. And the rate and the direction of that precession tells me the strength and sign of the interaction. Okay, and so that's this color plot here is showing the phase, and you're seeing it precessing over time. I find color plots a little bit hard to read, so we could also just sort of animate this and say, what is the local magnetization doing? It's rotating in different ways depending on the sign of my laser detuning from resonance. So that shows I can do either ferromagnetic or anti-ferromagnetic interactions. And again, the rate of this precession tells me the strength of the Ising coupling. And we can do a similar type of thing to map out the XY coupling with a slightly different initial spin texture. Okay, and so that is kind of neat. It shows us this tunability that, you know, in sort of a material, in the solid state, you're not going to get to just dial in what is my spin exchange versus my Ising coupling, but here we can just do that. Maybe I'll just briefly pause and ask, are there questions so far? If not, that's okay. Are there, yeah.
No, there are no questions in the chat so far.
Okay, that's no problem. Just encourage people to ask questions if there are any, but I'll continue. And so, so this kind of shows us we can tune the form of the Hamiltonian. We can realize either sign. And one thing that sort of I naturally want to ask when I talk about controlling the sign of the interaction, is it ferromagnetic or anti-ferromagnetic? I showed you we can pick that by looking at the dynamics. But you might more naturally want to ask also about the low energy states of the system. When I say, is it ferromagnetic or anti-ferromagnetic, the more intuitive interpretation of that is not which way do the spins precess, but do they want to align or anti-align? So, we thought it's a nice cross-check to maybe ask, can we prepare sort of a low energy state of the system, and what does that look like? And so the way that we can do that is essentially to start with all of the spins aligned along some magnetic field. To be precise, it's actually an effective magnetic field. That's just, we turn on a coupling between the two states. So that magnetic field, I called it H here. So HX would be the coupling, HZ would be the detuning of some drive field. And we can essentially, again, start with the spins aligned in somewhere in this XZ plane. And then slowly turn on interactions and see how that affects their state. Let me first, though, do the non-interacting example to orient you. So in the absence of interactions, we can do an experiment where we say, I'm going to sort of initialize the spins, you know, all pointing down, and then I'm going to slowly ramp to some final value of HX, and I'll plot the magnetization versus sorry, I'll start with a large value of HZ. I'll slowly ramp to some final value of HZ, and I'll just check what the magnetization is as a function of the tilt of my effective field. And as you would expect, as I sort of vary the tilt of the effective field, the magnetization follows. So that's the color here. Blue is down, red is up. If I now turn on interactions, let's say a ferromagnetic Ising interaction, and I do the same experiment. So now I vary again the tilt of the this effective field, but I have this ferromagnetic interaction on, then you'll actually see a change where there's a very, very sharp sort of knife edge between all of the spins wanting to point down and all of them wanting to point up with just a very small tilt of this field. And so that shows me that sort of is what you would expect for a ferromagnetic system, right? They want to lock together, and any tiny symmetry breaking field will make them point either all down or all up. Okay, and on the flip side of this, if I have anti-ferromagnetic interactions, this feature of the spin, this feature sort of washes out. So I can sort of parameterize what we're plotting here by a magnetic susceptibility, right? And basically measuring around Hz equals 0 here, the susceptibility of the system to small tilts in my aligning field. And we can now look at this as a function of the strength of the Ising coupling. And at some critical strength of the Ising coupling, you'll see the susceptibility, we expect it to diverge as we go from a paramagnetic to a ferromagnetic regime. And in fact, to the limits of our experimental resolution, we in fact see that divergence at the appropriate critical interaction strength. So that's approaching this phase transition to ferromagnetic. And so that matches nicely what we expect. One kind of fun thing you can do in this system is ask what happens if I do the same thing with XY interactions. And it turns out that this susceptibility plot is almost the mirror image of what I had for the Ising case. And it might not be totally obvious why, but actually we can understand this fairly well. So why does this plot have this symmetry? We can understand this fairly well by thinking about a simple limit where I imagine that all of the spins are uniformly coupled to the cavity. And if I had that, then I could relate, I can sort of write down, quite generally, I can write down the Hamiltonian in terms of some sort of weighted collective spin that I've called curly F here. But in the simple limit where the coupling is uniform, then I also have a relation that Fz squared, which is the Ising interaction, is basically the same as minus Fx squared minus Fy squared up to a term that depends on the total spin. And if I, for example, start in a spin polarized state and have permutation symmetry, then this term won't do anything. And so it makes sense that a ferromagnetic Ising interaction is much like an anti-ferromagnetic XY interaction. And so interestingly, you kind of see this same, essentially the Ising paramagnetic, the phase transition to the Ising ferromagnet, but you see it with anti-ferromagnetic XY interactions. So that is kind of, it's kind of a cute symmetry. Now, one thing that sort of I didn't like so much about seeing this is that if we want to study some many body physics in the system, you might actually like to get into a regime where the system isn't just behaving like one large collective spin, right? So we were curious, can you sort of get beyond this regime where the system acts like one big collective spin? And one way to do that is to add in some spatial inhomogeneity. Actually, we don't even have to intentionally add it in. If we're not careful in our experiment, there's some very small magnetic field gradient across the system. And in the absence of interactions, if you just look as a function of time, you start with the spins aligned, let's say along X, and look as a function of time, you'll see some phase wind across the system because of this small uncontrolled magnetic field gradient. If you turn on now, let's say, XY interactions in the system and do the same experiment. So I'm looking again now at the phase here as a function of time, and it looks very boring. The phase is basically not changing. And that's actually because the interactions are essentially protecting the coherence of the spins and kind of keeping them aligned. So this is something where if I have Ising interactions or no interactions, I see this phase winding across the cloud. If I turn on these XY interactions, they actually prevent the dephasing. And again, we can understand this by this relationship that Ising interactions are similar to XY interactions up to a term that depends on the total length of the spin. So what we have here is basically there's essentially an energy gap between manifolds of different total spin that tells you if you start in the spin polarized state, the XY interactions, because they include this energy gap, will help sort of protect you and keep you in this state where the spins are aligned. Ising interactions do not do the same thing. And so this is a nice illustration that it's not purely a system that we have to think of as a single collective spin. The XY interactions can help protect that spin if we want that. And that can be useful, for example, in quantum sensing applications. If you want to use the light to prepare an entangled state and you want to be robust against any spatial inhomogeneity, this could actually be advantageous. And that was first pointed out in some nice work from the group in Gilla. A neat thing within our experiment is that we can really directly observe, does the system dephase or not, and look at the spatial dynamics, and directly also compare the Ising versus the spin exchange case. Okay, so far actually most of what I've shown you can be understood in essentially kind of a mean field picture. And I want to get to something that looks a little bit more quantum, where you can directly really see the quantum physics at play. So let's actually add sort of one more wrinkle to this story. So far, I kind of abstractly treated the spins as though they were spin 1/2, but it turns out that was fine for everything I talked about so far. It turns out that we actually have a spin 1 system. Each of our atoms, the ground state, is a spin 1. And so that allows us to actually look at some richer physics. So for example, you can ask the question, what happens if I initialize the spin 1 system with every atom in the m equals 0 state? But naively, by kind of the picture I gave you of the magnetization of the atoms coupling to the polarization of the light, you might think that nothing will happen, right? If I start with sort of average magnetization 0. So maybe you can think about that for a moment. Will anything happen? So what we'll do is we'll turn on this spin exchange Hamiltonian with all atoms initialized in the m equals 0 state and see whether anything happens. Okay, so here's 100 repetitions of that same experiment. And what you'll see, what I'm plotting here is basically after turning on the light for some period of time, an image of the atoms in these 3 different states, the -1 atoms, the 0 atoms, and the +1 atoms. And what you'll see is that, first of all, you'll notice sort of large fluctuations from shot to shot of the same experiment. But sometimes you'll see quite a lot of population in the -1 state, and that's always correlated with some population in the +1 state. Okay, and this is actually something we can understand quite well. If you wanted to sort of write down a model for this, I would say that, yeah, is there a question?
Yeah, sorry. Yeah. So there is a question that's related to this and mostly the previous slide. The question is, in the experiment, was there a difference between curly F and the actual F? And if so, isn't that a difference that would make this not just the dynamics of a collective spin?
Yeah, so that's a great question. So in the experiment, there actually is a fairly strong inhomogeneity in the couplings of different atoms to the cavity. That varies by at least a factor of 4 or more for different atoms. So yeah, and so this sort of equation I wrote down here is oversimplified. Nevertheless, and so this sort of gives some intuition, but it really is a many body system in the sense that there are these spatially inhomogeneous couplings, and the fact that kind of this picture from the this equation I gave here still gives a rough intuition. Partly you can even think of sort of at the level of if I think even just about a pair of atoms, the fact that I have a spin exchange interaction basically means I have some energy splitting between kind of a singlet and a triplet configuration of 2 spins. And that means that if I start in a symmetric state, there'll be kind of this cost to changing to the singlet state that's anti-symmetric. And so even without having this perfect permutation symmetry, the spin exchange interactions will tend to protect the coherence. But yes, we do have inhomogeneous couplings. And that also means that in principle, I showed earlier the sort of theoretical dynamical phase diagram of this system with these non-equal but separable couplings. That should be something that is possible to explore more thoroughly in this system. So yeah.
Thanks.
Great. Was there another question at this point?
No.
Okay, thanks for the question. Yeah, it's much more interesting when it's a dialogue and not just a monologue. Okay, so good. So I told you now we have actually a spin 1 system, which adds some richness. And in particular, we can see this kind of a spin mixing process if we turn on spin exchange interactions, where if we start with all atoms in the 0 state, we can see correlated population growth in the +1 and the -1 states. If you want to kind of write down the model for this, I could sort of, I find it useful to think of these 3 different states roughly as 3 bosonic modes. I'll call the 0 state C and the others A and B. And roughly this flip-flop type interaction, the F plus F minus interaction, means I can take two zero atoms, so that's like a C squared term in my Hamiltonian, and create a pair in the +1 and the -1 states. Okay, and if you kind of do a little bit of algebra, you can convince yourself that this system, I can do some transformation to basically two decoupled oscillators that I called X plus and X minus here. But it turns out this ends up looking like basically a system of inverted harmonic oscillators or negative mass harmonic oscillators, which has an instability to forming actually these correlated pairs of atoms in the A and the B modes. And so as you would sort of expect from this idea that there's an instability, if you look as a function of time, one sees in the system an exponential growth of population in the +1 and the -1 states. That's shown in blue here. And this is something that, similar physics has actually been studied, for example, in systems of Bose-Einstein condensates, where there are direct collisional interactions that turn two zero atoms into a +1 and a -1 atom. And those have actually been harnessed to make highly entangled so-called twin Fock states, where I have exactly the same number of atoms in +1 and -1 that are actually resources for quantum enhanced sensing. It's also kind of, you can think of it a little bit like creating correlated photon pairs in a nonlinear crystal, right? So this is a resource for making entangled states. The fact that we can do this in a way that is mediated by light is interesting for a couple of reasons. One is actually very fast compared to collisional interactions, but also because this is happening in a way that is optically controlled in the sort of millimeter scale cloud of atoms, you can start to ask the question, can I take advantage of this optical control to control, for example, the spatial structure of these correlations? So that's the direction that we are currently exploring. And in order to do that a little bit more cleanly, we're now working in a system where we have an array of small ensembles in our cavity. So we have, in the experiments I'll show you, there are 18 sites. Each site has 1,000 or 2,000 atoms in it. We still like to have many atoms per site because it helps us out with a collective enhancement of essentially the atom-light interaction strength and the corresponding atom-atom interaction strength. So we have these 18 sites. And what we'd like to be able to do, well, ideally, is maybe control the interaction between arbitrary pairs, or more modestly, so let's say dial in any, let's say, translation invariant structure of the coupling. So can we start to control the couplings versus distance in the system? Okay, so in order to do that, that actually already sounds fairly ambitious, arbitrary control of the couplings versus distance. But it turns out that that's not so crazy. So the first step to doing this is actually to turn off the all-to-all interaction. So as a starting point, what we do is we make the interaction more local by applying a magnetic field gradient. So in the presence of a magnetic field gradient, this pair creation going from two zero atoms to a +1 and a -1 is only resonant if the pair is formed locally, right? If the pair were long range, that would not, since going from 0, 0 to plus and minus would not conserve energy because of the gradient. And in fact, we see that. So what I'm showing here is a plot of the correlations between the number of, something is weird about the axis label. I don't know what's going on with the numbers here. Oh yeah, no, it's fine. Okay, yeah. So the correlations between the number of +1 atoms on a given site and the number of -1 atoms on a given site. And what you can see is that these correlations in the presence of the magnetic field gradient are only on the diagonal. That's saying that these pairs are forming locally. If I had no gradient, the correlation would be completely long ranged and the plot would look boring. So I showed you the one with the gradient. And now what we can do, though, is we can controllably turn on interactions at a particular distance by sending in not a single frequency, but two frequencies of our laser field. So if we send in two frequencies of our laser field, that frequency difference can sort of bridge that energy cost of preparing a non-local +1 -1 pair, right? When the frequency splitting matches the energy shift due to the magnetic field gradient at a given distance. And so we see that when we turn on two laser frequencies, we see that correlations start to appear off the diagonal at a particular distance that's set by the difference in the control field frequencies. So that now you can ask, what happens if I vary the frequency, right? So here's, I've now collapsed the 2D plot into just, this is, correlations versus distance. Here I'm varying the frequency, and you can in fact see the correlations appearing at the distance that is set by the laser frequency. And you can even kind of zoom in and see we have really quite fine control. I was actually pretty impressed when I saw these data that my students are actually able, by dialing in the frequency, really to turn on interactions at site, distance 10 and not distance 11 or whatever. So, so this is looking like really a very powerful tool for being able to dial in the structure of the interactions. It's technically straightforward to send in multiple frequencies. And so you could really then, we focus so far on understanding the case of one, but then that actually allows you in principle to have arbitrary couplings versus distance in this system. And one of the things that kind of motivated us to think about this was in fact, this idea of how could you build some models that might give rise to fast scrambling. And so the kind of dream that we had been thinking about is essentially if I want to sort of have non-local interactions, but I don't want them to be so simple that it's just a single collective spin, but I do want information to sort of spread efficiently with just a few different laser frequencies. So what we would like to do, and this is still an outlook, I won't be showing data on this today, but we'd love to be able to dial in, let's say I have nearest neighbor, second neighbor, fourth, eighth neighbor hopping. And so you bridge many distances in sort of an efficient way, and you can ask what would a model like that do? And so we're thinking about this also in collaboration with Steve Gubser at Princeton, who pointed out this is a particularly interesting model if you have the ability to sort of control, do the interactions grow or shrink with distance? So I would imagine having these power of two interactions, and if they shrink with distance, it would look almost like a linear spin chain. So if I initiated the system with an excitation in some place and asked how it propagates, you would see this kind of a light cone feature. But if you then tuned this exponent to 0, so that you have kind of equal interactions on these various different length scales, then that light cone would start to break down. It starts to look kind of logarithmic in terms of time versus distance. In fact, you can't solve this exactly for more than some tens of spins. With a group of Andrew Daly, they did some matrix product state calculations to ask, what are the scrambling properties of this? But sort of the best we can do to go to large system sizes is ask in some semi-classical limit, what is kind of the Lyapunov exponent and what does that tell us about the scrambling time? It looks promising for being a fast scrambler in the sense that this scrambling time is logarithmic in the system size. And then just to add one more sort of step to this, in principle, if you now change this exponent so that interactions grow with distance and look at the dynamics of the way that excitations spread, it turns out that it is best described as thinking of these sites not as being on a linear chain, but as being sort of the leaves on some tree graph. And you can actually think of this tree as essentially a discretized model for a hyperbolic space. And so this is kind of, one can think of this as a way where just by tuning some laser frequencies, you would effectively almost change the geometry of your system. And at the transition between these two geometries, everything is kind of strongly connected to everything, and you would expect to find a fast scrambler. Okay, so I think that gives a flavor for hopefully the fact that sort of these optically programmable long-range interactions can let you explore some neat physics that are maybe not so natural to realize in the lab, but that are now hopefully about to become possible. And this is interesting for a number of reasons, but in the context of a chaos seminar is interesting in the sense that it could be a route to fast scrambling. Since I mentioned fast scrambling, I should just briefly say that, even if you can do that, you might ask, how do you probe it? And there have been a lot of kind of nice recent experiments showing that it's possible to probe scrambling by various methods. One is kind of saying, well, chaos is all about sort of a butterfly effect. How sensitive is the system to perturbations? And if you can evolve a system forward and backward in time and perturb it along the way, that can be a knob for testing by forward and backward in time, I mean applying H and then minus H. That can be a way of probing sensitivity to perturbations. And one tool we have in the system is the ability to control the sign of the interaction. That would be a natural thing to start to explore. Another kind of general approach to probing chaos in these quantum simulators involves exploiting, classically we have this notion of chaos as being about sensitivity to initial conditions. And so there's sort of a class of techniques that involve preparing random initial states and watching how they evolve. And there have been nice trapped ion experiments in the group of Rainer Blatt and Christian Roos, inspired by theory from Peter Zoller's group. We've also collaborated with Xiaoliang Qi and some related ideas. So this sort of method of sort of preparing many different initial states is something that you've seen. We're kind of starting to have that toolbox in terms of being able to locally manipulate and prepare spin textures in the system. So that's another approach that could be explored. And lastly, there's a set of approaches that involve teleportation protocols. And I won't say too much about this, except that the key resource that one needs to probe scrambling by this third method is actually what's called some kind of an entangled state. In particular, there's a state called a thermofield double state, which is I have two systems and each one by itself looks thermal. But when I look at the thing together, it's in a pure state. And it turns out that in principle, the pair creation process I showed makes actually exactly this type of state, in the sense that if I were to look at +1 or -1 alone, the fluctuations should look like those of a thermal state of a harmonic oscillator, but the system as a whole should be a pure state. Okay, so we haven't sufficiently carefully characterized the state to prove that it is this, but if you write it down on paper, that's actually the type of state you get. And so that may be a neat resource also for applying some of these methods to probe scrambling. At this point, if I have time, I would love to shift gears and say a little bit about the system where we can make local interactions. But maybe I should pause and ask, are there questions and is there time?
There's definitely time. And I
Okay.
guess I have a question about these arrays of atomic clouds that you were just talking about.
Yeah.
So if I got it correctly, in each of these sites, you have about thousands of atoms, something like that. So does that, I don't know if this is kind of a too theorist question, does that affect like the local Hilbert space dimension that you have on each site? Or is it like, in each site, they still have like a 2-level system or a 3-level system? Is that something that one could think of, changing as you change the number of atoms in each site?
Yeah, so it certainly changes the local Hilbert space dimension. Roughly, if you think of each site as having kind of a permutation symmetry, it means that the dimension is kind of order n, where n is the number of atoms on the site and not 2 to the n. Ideally, what you would love to do, and I kind of hinted at this actually in this like phase diagram I showed earlier of these separable spin models, you would love to be able to actually tune from having just a single, spin half or spin 1 on a site all the way up to like a large collective spin, and that thereby kind of tune from something more quantum to something more classical maybe. Technically, the challenge with that is that, as I mentioned, right now we're benefiting from some collective enhancement of the interaction strength. So we are in a regime where our atom cavity coupling is in the so-called single atom strong coupling regime. But it turns out that for these types of experiments, so there's a figure of merit called the cooperativity, which is larger than 1. But you'd like it to be sort of much larger than 1. And in our system, our cavity mirrors are a little bit dirty. And if they weren't dirty for a single atom, it could be around 100, which is quite good. But right now we're benefiting from having sort of 1,000 atoms to have it even be, several thousand, and that actually helps. So I would say it's kind of an important challenge to ask the question, how can one get into a sort of even more deeply quantum regime where you have fewer atoms or 1 atom on a site? And that's, something we're also thinking about. But for now, we're already quite happy to kind of explore this. Maybe you can understand things a bit more semi-classically when you have these larger ensembles. In this, I think of this right now in this pair creation physics as I sort of have these 3 modes on a site, and each one has some finite maximum occupation though, right? Yeah, so I don't know, does that answer your question?
Yeah, absolutely. Yeah. Thank you.
Great.
So there are a few more questions, but maybe we could leave them for the end.
Okay, sure. We can do that. So yeah, let's see. I had just put up some pictures of kind of, ways you might want to probe scrambling. One thing that, I've focused on the neat things you can do with these kind of exotic non-local interactions. But if you do want to study, chaos, let's say, or other many-body physics in systems with local interactions and ask, for example, how does information spread in this, perhaps in a system with local interactions. It's also kind of natural to have, instead of these photon-mediated interactions, there's a way that's sort of more natural for studying, let's say, spin chain physics, which is coupling atoms to Rydberg states that give you interactions that are sort of on the few micron scale. One of the things that we've been working on is realizing interactions that can still be something where you have essentially a spin that is ordinarily non-interacting, but where you can locally and dynamically control the interaction with light. Okay, so the basic idea is in order to get an interaction, we take a ground state cesium atom, and if you excite it to, let's say, a state with principal quantum number n equals 43, this is kind of a scale picture of how much larger the atom is. The van der Waals interactions between these atoms scale as the principal quantum number to the 11th power. So this is a good way to get strong interactions on the few micron scale, it turns out. And there are actually a few different ways that these Rydberg atoms are being used for experiments in quantum many-body physics, which might involve encoding a spin on the ground to Rydberg transition or in a transition between Rydberg states. What we've been working on, though, is having spins encoded in stable ground states, and in such a way that only when the light is on does one have an interaction, and one can tune aspects of that interaction using the laser field. So this is a method called Rydberg dressing. And so in this experiment, we encode kind of a spin in two ground hyperfine states of cesium, and we off-resonantly couple one of those states to a Rydberg state. And I can think of this as if I just had a single atom, this laser would introduce some AC Stark shift that would shift the level of that atom, or also if I had two atoms that are very far apart. But if I bring my two atoms close together, the AC Stark shift is actually suppressed essentially by the impossibility of exciting both of those atoms. So there's sort of a process at fourth order in perturbation theory that goes away, that gives rise to some distance dependent energy of this state where both atoms are in the up state. And I can think of this as an Ising interaction. We've so far been looking at this in just a gas of atoms. Eventually, you might like to have a sort of an ordered spin chain. And one way that you can see in this gas of atoms that interaction is present is just by saying, well, if I have an Ising interaction, that means that any given spin should precess at a rate that depends on how many surrounding spins are spin up, or on the Z components of the surrounding spins. So if I look at some region of the cloud and I look at the average magnetization, what we'll do is we'll sort of initialize the system with different tilts of the magnetization, and turn on the light and watch how this evolves. And what we'll see is kind of a twisting behavior, which is to say if more spins are up, the precession rate is faster. If more spins are down, it is slower. And that's a signature at the mean field level that we've turned on these Ising interactions. Those are data, by the way. We can also kind of look now spatially as a function of position in our cloud of atoms. So horizontal here is position in our cloud of atoms. The vertical are different tilts of the initial magnetization. And in this particular experiment, the laser that's turning on the interactions has some kind of Gaussian profile that tells us interactions are strongest here in the center. And correspondingly, this twist is also strongest in the center. You can see that by the strong sort of blue at the top, red at the bottom, as a function of the tilt. Okay, so that kind of shows we can locally control these interactions in a way that's set by the intensity of the light. One reason this is actually interesting is if you look now not just at the mean field dynamics, but at what happens to quantum fluctuations. This type of twisting can squeeze quantum fluctuations. And this has been done in other systems, like actually cavity systems that I mentioned earlier. But being able to do this with local addressing would be advantageous, for example, for making, let's say, arrays of entangled states. But there's actually an interesting question about if you want to make actually like a long-range entangled state with only local interactions, there might be some limitation in the fact that if I have Ising interactions, this guy, whether it's up or down, will affect the phase of this spin, but this spin's phase won't affect any spin down the line. So the interactions, the effect won't spread unless you have some, say, transverse field that doesn't commute with the Ising term. So a second ingredient that we've been building up is the ability to make a transverse field Ising model, okay? Where we can, let's say, we do it for convenience, it turns out, that we like to alternate between applying Ising interactions for a short time and then applying a transverse field for a short time in a pulsed fashion. The transverse field is just a microwave coupling between the two spin states. And that gives us some kind of a Floquet transverse field Ising model. And so far we've worked in a regime where the alternation is fast enough that it essentially mimics a static transverse field Ising model. At the mean field, you can sort of think of this, I've written down some kind of a mean field model for what we would expect to happen. And if, for example, if I have just the transverse field and no Ising interactions, what we expect to happen is very simple. You'd expect spins to sort of precess about the x-axis. I've shown that here for just a few cycles of this Floquet sequence. And I can think of this as sort of precessing about a fixed point, which represents the ground state of this Hamiltonian. So the ground state is all spins along x, and that manifests as a precession about the x-axis. If I turn on Ising interactions, then actually you start to see in these mean field dynamics precession about two new fixed points that are above and below the equator of my Bloch sphere. And a neat thing about this system, actually, we're looking at a sort of, I showed you sort of each of these pictures is at one point in our spatially extended cloud. And I should say, sorry, let me take a step back and say, we can think of these dynamics as signifying kind of a bifurcation in these fixed points, signifying a transition from a paramagnetic ground state to two ferromagnetic ground states. So we're kind of learning something about the phase from the dynamics. And if you actually look now as a function of position in this cloud, I'm again showing one of these plots where the vertical is sort of the initial tilt of my magnetization. The color is the phase. The white region is the place where the phase stayed fixed. And you can actually see this bifurcation in the fixed points happening as a function of position in the cloud because of the spatially varying interaction strength. So I think this shows kind of a couple of nice features of these optically controlled interactions, the spatial control and also the dynamical control. And so we're interested in kind of putting these together in a variety, applying these in a variety of different contexts. One kind of neat direction is that by having some spatial variation in the interaction strength, there are actually proposals for sort of mimicking quantum dynamics in curved space. Also just taking advantage of the ability to explore this Floquet system, alternating between the interactions and the transverse field. So far, we sort of mimic the static model, but there's a rich phase diagram once it starts to vary how long I apply the interactions or the field. And particularly if I do this in the more ordered setting of a 1D spin chain, which is the direction that we are moving in the system. So there's also work on studying, for example, Kapitsa phases and lots of sort of interesting non-equilibrium dynamics that could be explored here. And lastly, we again have control over the sign of the interaction just by choice of laser properties and Rydberg states. So this is natural also. We were working with ferromagnetic interactions, but one could easily make them anti-ferromagnetic, and that's great for studying frustrated models and exploring some questions in combinatorial optimization. So these are all directions that we're going. I think at this point, I'll just summarize and say, I've shown you these two different physical systems where we have optically programmable long-range interactions of various kinds. I've showed you, particularly in the cavity system, that we can program the form of the interaction, the sign of the interaction, the distance dependence of the couplings, and some neat effects where interactions can protect the coherence of the collective spin. And we're interested, so far that was protecting coherence, but we would love to also see information get scrambled. So that's a direction for the future, and lots of neat directions more broadly in studying non-equilibrium dynamics with these optically controlled interactions. So with that, I think maybe I will just thank my team. Eric and Avikar have done these latest cavity QED experiments, building on earlier work by Emily Davis and Greg Benson, and these folks in blue led the Rydberg experiments that I talked about at the end. And I'll take questions.
All right, thank you very much, Monica, for such an interesting and clear talk. So we have a few questions, as I was saying before. So we'll get right to it. So one of the questions, I guess this was, you were mentioning all these kind of different schemes to probe scrambling. One of the questions is, what would be the ideal scheme in order to probe scrambling in the particular platform that you were describing?
Yeah, I would say which is ideal is to some extent going to be informed by, yeah, there are questions about sort of the technical details of the implementation. So maybe let me come back to this slide if I can. Where was that slide? Somewhere here. So I would say that the ones that are sort of probably most natural to implement are these first two. So I showed you before that we can switch the sign of the interaction already. And what I would love to do in principle is something where we say, I have some simple operation, like a local spin rotation. And what I would like to do is almost like some kind of tomography of the Heisenberg operator after some time evolution, which let's say I call my operator W. What I would like to measure is something like e to the IHT, W, e to the minus IHT, right? So I would like to sort of measure that Heisenberg operator. And you could imagine directly implementing that. Like literally I evolve with one sign of the interaction. I do a local perturbation. I evolve again with the other sign of the interaction. And then we have lots of ways of sort of measuring in different bases, depending whether we do another spin rotation before we image. So that would be, I think, a neat thing to sort of really kind of watch how that Heisenberg operator grows in some way. The main question is, of course, I've been kind of assuming that we have a perfect unitary evolution and that we can perfectly switch the sign, right? So technical limitations we might worry about are, there's always some dissipation, if nothing else, from the fact that if you're not in the regime of sort of infinitely high cooperativity, which is our figure of merit, there's some chance that a photon leaves and carries away some information. So we make the cooperativity large, but there's some dissipation. And then there's also a question of how perfect we can make the sign reversal. So I think we would love to try it. And to some extent, I think we have to see how well it works. This idea of sensitivity to initial conditions is also something that would be very natural because we're also preparing different initial states. There's some question about exactly how to do this in the case where you don't just have a single spin, but you have a small ensemble on each site. This gets to a little bit to the question that I think you, Pablo, asked about sort of what is the local Hilbert space dimension. Ideally, you would start with some random unitary on that sort of order n dimensional Hilbert space, and that I don't know how to do. We can do kind of simple things like rotations. So so that's kind of maybe an open question, is whether with the simpler set of tools we have, you can still do some approximation of this kind of protocol. And my instinct is yes, but it would need to be thought through. So.
Cool, excellent, thank you.
And then I'll just say this one is more speculative. I don't know exactly what to do with this, but it seems we naturally make these thermofield double states. So yeah. And if anybody in the audience wants to think about it more, I'd be happy to.
All right, excellent. Challenge for the audience.
Yeah.
All right, so I guess another question is, can you also model strong confinement like quark gluon stuff when the interaction grows with distance?
That sounds like an interesting question. I would love to hear more about it if whoever asked has like concrete ideas. So we certainly can make the interaction grow with distance. My sort of vague understanding was that to study things like confinement, you would like to have some kind of dynamical gauge field, which, or at least I know there are proposals for sort of engineering dynamical gauge fields to study phenomena like that. That's not something that we're currently doing, although there might be some directions combining the spins and photons to explore that. Yeah, I think whoever that is, if they have like a concrete idea, I would love to get an email about it. It's not something we thought. It sounds neat. Yeah.
And there's, I guess, finally one question about the Rydberg part, which is when you turn on the Rydberg dressing, is this done adiabatically? And if not, do you have Rabi oscillations in that process?
Yeah, so that's a good question. So this, so this light is something like 20 megahertz detuned from the Rydberg state. And even kind of without trying, just the sort of time it takes for the light to turn on in the way that we switch it with an acoustic optic modulator is kind of on the microsecond or hundreds of nanosecond scale. So it is somewhat, it's intended to be adiabatic. And otherwise, that's right, you would expect some oscillations that you want to avoid. So yeah.
All right.
I think I also have an additional question, which is related to the previous one about directly probing scrambling. Would it be possible to devise some scheme to directly measure entanglement entropies within these setups?
That's a great question. So, I think one thing you might imagine, okay, so I think in principle, and I'm always worried about dissipation, but let me just say in principle, with this scheme for sort of controlling the distance dependence of the couplings, imagine that you could imagine having like two decoupled 1D chains where I have, some Hamiltonian within the chains, but then I also have some like long range coupling that allows me to turn on spin exchange between the chains. And I think that would be kind of the analog of what's been done in these beautiful experiments in Marcus Reiner's group, where they have two, adjacent Bose-Hubbard chains, and they have turn on tunneling between them to kind of interfere the sites. So, that in principle, seems like it would work. In practice, I think the main question is kind of how coherent do you need the interactions to be for that to actually work well? There are also some proposals for measuring entanglement entropy that involve some kind of an ancilla qubit that interacts with a many-body system. And I'm not remembering all the details here, but there are ways you could imagine using the cavity to have sort of a one-to-many coupling that might be relevant for some of those methods.
Okay, great. Thanks a lot.
All right. So I think there are no more questions, so that will conclude the seminar for today. So thank you, Monica, again for giving this great talk and participating in this series. So for us, it was a privilege to have Monica as our official, last official speaker of the fall series of this Quantum Chaos seminar. However, we do have one more event next week, and we invite all of you to join us on Thursday, December 3rd, I guess, the usual day at the usual time, where we'll have a bonus event where Peter and I are going to give short talks. So I'll just say, Peter, would you like to say the title of your talk?
Okay, yeah, I'll be talking about thermalization and scrambling in dual unitary circuit models.
All right, awesome. And I'll be talking about quantifying sensitivity to imperfections in quantum simulations. So we hope you'll join us next week. Thank you, Monica, again. And